This is part one of a multi-video series in which we will build an end-to-end machine learning application that will predict the gender of a person based on an image. In this first part, we will train the model and evaluate its performance. In the second part, we will expose the model as an API and host that API. And then in the final part, we will build client-side apps using Flutter. So without any further ado, let's get to it. Okay, so the first step is to go to the description of the video and download a zip file, or download the zip file. And when you extract that zip file, you will get one root folder that's called gender. And then within that, you will have two subfolders, one male and one female folder. And each one of these folders has the images. And the reason why you need to download and extract this is because this is our data set. And once you have that taken care of, you can open your text editor in the same folder that you have extracted that gender folder, and then you can create a new file. So I'll be using VS Code for this, so file new, and you can save it as train.py. And for the model training, I will be using TensorFlow. Specifically, I'll be using TensorFlow version 2.3. So to prevent any problems, I would recommend that you install the same version. And when it comes to CPU versus GPU, I'll be using the GPU version of TensorFlow. However, the code that we'll be writing in this video will run on a GPU or non-GPU installation of TensorFlow. So once you have everything installed, you will also need matplotlib, and that's about it. Matplotlib and pathlib. So the first step is to import our library. So import pathlib, import matplotlib.pyplot as plt, import numpy as np, import TensorFlow as tf, import from TensorFlow import keras, and then from TensorFlow.keras import, from TensorFlow.keras.models import sequential, and from TensorFlow.keras import layers. TensorFlow.keras and from. And you can see that it's highlighting it in yellow, so I'm just going to configure the Python interpreter. Okay, so once we have all of our libraries imported, the next step is to specify the path to our data. So to do this, I'm going to make a new variable called datadir, and then I'm going to have that equal to pathlib.path, and I'm just going to have it gender. And you may be wondering why I'm doing this pathlib.path thing, and the reason for that is because TensorFlow, the TensorFlow function create dataset from directory, accepts pathlib, and I've tried using it as string, but I get some errors, so I'm just going to do it like that. And then I am going to, once we have this done, that's why I was highlighting it. Okay. Once we have this defined and taken care of, the next thing that we're going to do is we're going to define some constants. And actually, just for formatting, I'm actually just going to do that up here. So batch size is the first constant that we're going to define. It's 32. And that's the batch size of our training. And the next one is image height. And for this, I'm just going to use 398. And then for image width, I'm going to use 309. I'm just going to... Okay. And now that we have that, we're going to create our data set. So train _ds space equals space tf.keras .preprocessing .image dataset from directory, and this takes in a few parameters. The first one is the path to our dataset, The second one is how much to use for validation. The next one is what we're using this data for, which is a subset. The one after that is the seed, then the batch size, and the image height and the width. So I'm going to type data dir. Then after that, we're going to do validation underscore split is going to be equal to 0.2. Then after that, we're going to have subset equal 123, or not subset, sorry, subset equal to training. Then we're going to have seed equal to 123, and we need to put commas there, obviously, like that. And then after seed, we're going to do image underscore size is equal to, this is a tuple of image height, comma, and then image width. Once we have that tuple on the next line, we're going to do batch size is equal to batch size, the constant, and close that off. And I'm getting some sort of error here. Let me see what it is. Validation split. Okay, it's just giving some thing. We'll see what the error is when we come to runtime. But the error when we come to runtime, or is it the parenthesis? Let's see. Okay, here we go. So I accidentally put a bracket instead of parenthesis there. And that's actually extra. Okay, now once we have this, I'm just going to copy this over here and rename this to val, and then same stuff, data dir, validation split, same thing, but this we're going to change to validation, and then just the same stuff. After that, we're going to define a variable called class name, and that's going to be equal to train ds.classNames. And it's going to get these class names because it's going to realize that there's two subfolders inside the root dataset folder, and those will automatically become our class names. Once we have that done, we're going to load in AutoTune, which will optimize our dataset and make sure it is not bottlenecking with the I/O. So to do that, we're just going to do AutoTune here. Go AutoTune is equal to tf.data.experimental.AutoTune. And then we're going to do train underscore ds is equal to train ds.cache, like that, dot shuffle 1000 dot prefetch buffer underscore size is equal to AutoTune. So it's going to AutoTune that, and then I'm just going to copy that here like this and just change that to val, like that, and then just put that over here like that. And once we have that auto-tuning taken care of, we're going to add a normalization layer. And the reason for this is to normalize the pixels. So normalization layer is equal to layers dot experimental dot pre-processing dot rescaling. And we're going to divide we're going to do 1 dot divided by 225, like that, and layers dot experimental dot pre-processing. Did I spell everything right? Let's see. Okay. Experimental. Okay. And then we're going to do normalized underscore ds is equal to train ds dot map. And then we're going to do a lambda function here. Lambda space, and then just x comma y colon like this, and then we're going to do layer X like that, and then just come over here and do Y and spell it right like that. Lamb. There we go. And let me just explain what we just did there a little bit. So here, again, we're caching the data so it doesn't become a disk bottleneck. Here we're defining the normalization layer. And then here we are normalizing our data set. Once that is taken care of, we're going to do image batch. Label batch is going to be equal to next. And then we're going to iterate over normalized, not layer, ds. And here, normalized ds. We're, in that line, 44, we are defining image batch and label batch, and that is just an iteration over normalized data, or normalized data set, normalized ds. And then after that, we're going to do first image, just for our referencing purposes, is going to be image batch 0. And now we're going to print np.min, and the first image, this is just to make sure that everything is going right, and then np.max, and then again on the first image. Not like that. First image. And the reason why we're printing this is to make sure that the shape of the image is correct, that it's been sized correctly, and all of its properties are correct. And then we're going to define our constant number of classes. So num classes is equal to 2, just like that, very simple. And now it's time to define our model. And in this model, we're going to be using data augmentation because our data set is relatively small. And data augmentation is a technique that we will be using to make artificial data by applying transformations. And the way that this works is that it will take our real data and then it will duplicate that data, but it won't be identical. It'll add rotations, reflections, transformations, etc. to make the data more data, but still useful. So we're going to define our data augmentation layer. So data augmentation, we're going to have this equal to keras.sequential here. And just like this, just open it like that. And we're going to have a list. So list open like there, and then we're going to do layers.experimental dot pre-processing dot random flip, and this is going to flip them randomly, and we're going to flip them on the horizontal axis. And then input underscore shape. Input shape is again a tuple of image height. I'm just gonna copy it from there to keep it consistent. And then I'm gonna not like that. Image height, that's one of our layers. But first we just have to add a by 3, and the by 3 is because our image is a color image, not black and white. And once we have that, we're going to, since it's a list, just comma, and then we're going to add a new transformation, layers.experimental.preprocessing.random rotation. We're going to do 0.1. So this is a transformation of rotation that we're applying. And then we're going to do layers.experimental.preprocessing.random zoom. So right there, random zoom. And again, just 0.1, and then just comma. And I'm just going to check this. All right. And this is our data augmentation layer. And we're going to call this layer in the beginning of our model. So now let's go define the actual model. So model is equal to a sequential model, because we're using the TensorFlow sequential API, and brackets, not curly braces. And back over here, formatting it nice. All right, and then we're going to put our data augmentation, just what we defined over here. Then our next thing, we're going to define a new layer. So layers dot experimental dot pre-processing dot rescaling, and then 1 dot divided by 255, and then a comma because it's a list. Layers dot con2d, and then we're gonna put the feature size 16 by 3, and then we're gonna have padding is equal to same, and then activation is equal to ReLU. And we're just gonna write this code out now, and I promise I'll explain it when we're done writing the whole model, because it'll make way more sense there. And then we're gonna do layers dot max pooling 2D, and just like that. And now what we're gonna do is we're gonna just duplicate this a little bit with a comma. We're gonna duplicate this 3 times, so 1 or 2 more times, because including, and then we're just gonna change this feature size to 32 here, and then 64 here. And then at the end of this max pooling 2D, we're gonna add a dropout to prevent overfitting even further, which is also the reason why we put the data augmentation layer 0.2 for the dropout. And then we're going to do layers dot flatten, because we need to flatten them. And then layers dot dense, like this. We're just going to put 128 activation equal to ReLU. And then layers dot dense, finally, num classes. And this is our final model here. Let me just scroll up here. So let me explain this. So at the top here, we are calling the data augmentation that we wrote here, which is flipping, rotation, and zoom. Then after that, we're calling a convolutional layer with a max pooling 2D. So I like to call this a convolutional set, because most of the time when you use a convolutional layer, conv2D, you will use max pooling 2D. And then we're just doing the same thing, because our neural network here is having these many hidden layers, and we're increasing the feature size each time, because that is a standard practice to increase the feature size as you go on. Then we're dropping out here to prevent overfitting, which is, again, also the reason why we did data augmentation. And the reason why we could have overfitting is because we have less training data. Then we're just calling a dense here, and then we're densing the num classes. So once we have our model defined, we're going to compile it. So model.compile, and we're going to do optimizer is equal to Atom, and then loss is equal to tf.keras.losses.sparse categorical cross entropy, and it should be camel case. I guess the autocomplete hasn't taken care of that. Sparse categorical cross entropy, and then we're going to do specify from logits equal true, just like that. And then we're gonna just make a new line here, and then we're gonna do metrics accuracy. And then this is our compile. This is our compile function with the equal sign. This is compile, and now it is time to train our model. But before we do that, let's just print out a summary of it. Summary, like that. And then we're going to define one more constant. Epochs is equal to 15. Epochs is how many times to iterate over the dataset. Then we're going to do history is equal to model.fit. And here we're going to specify the data to fit on, so train underscore ds, like that, and then validation data equal to val.ds like that. Again, comma. And then we're going to do epochs equal to epochs like that. And this is our compile or our fitting function to fit the model. And instead of doing model.fit, I used history. And the reason for this is so we can use history as a callback. And before we use that callback, we're just going to save the model to save dot. I'm just going to do like this, gender. Let's give a string. I'm going to save it to gender dot h5 like that. Very simple. And then we're going to make our plots. And to make these plots, I am actually just going to use code from TensorFlow documentation. So TensorFlow docs, if we come over here, learn more over here, and then see the tutorials. If I go images, image classification, just going to come down here to visualize the training results. And a lot of this, by the way, is from the docs because a lot of TensorFlow is very similar. And just going to paste that there. Again, just straight from the docs. We use the history callback. Everything else is the same. And this is our file. And before you start the training process, just a few pointers here. Number one, if you're using a GPU, make sure that there are no GPU-intensive processes running. So to do this, open a command prompt as administrator or terminal, and then type in NVIDIA -SMI, and you can see if there are any VRAM-intensive processes. And as you can see, I have 7,000 megabytes out of 8,000 megabytes being used, and you never want to train like this. But the reason for this is actually my screen capture. So when I start the training, I'm going to pause the screen capture and bring it back. But once you figure out what processes are using the VRAM, you should end them. The second thing is if you're using a GPU, if you have any overclock set, even though you think that that overclock is extremely stable, it may be stable in other apps like games or creative apps, but TensorFlow, I've experienced myself, TensorFlow throws some syncing error. So just for safe practice, I would recommend removing those overclocks for the training. And the final pointer, again, relates back to number one, is don't have any screen cap software running. And that's about it. So now I'm going to stop my screen cap software and then just run this file as I would any other Python file, and I'll be back when it's done. Alright, and when the training is complete, you will have a gender.h5 file in the same directory as your Python file, and you will also see some graphs. And just to terminate the program so the GPU would become normalized, I saved those graphs and ended the program, but the graphs will look something like this. And on the left here, we have training accuracy in blue versus validation accuracy. And on the right, same color combination, but for loss. And looking at this kind of graph, this is about the same. This is about the right kind of graph you would want to see. And the reason for this is the training and validation loss are both going down and they're about the same. And for accuracy, they're about the same. They're staying on the same thing. And the reason why this is good is because this means that there was no overfitting. And that is exactly why we did the dropout and the data augmentation. If we wouldn't have done those, there would have most likely been some sort of overfitting. But now that we have that model, let's actually use that model. So I'm just going to come over here and make a new file, and I'm going to call it useModel.py. And to do this, just to start off here, I'm going to come over here and just import all of this. And then what I'm going to do is we're going to type image, or img for short, is equal to keras.preprocessing dot image dot load image, not load image, load img like that. And then we're going to specify the path to the image. So to just get the image, I'm going to come over here and just search this phase does not exist, or this person does not exist, and I'm just going to come here and save this image to that. I'm going to save it to downloads for now, and it's a GIF file, and I'm just going to come over here, and then I'm just going to come over to my downloads folder, which I'm not going to put on the screen for obvious reasons, and then just copy the image over to here, and I'm just going to copy it into the directory of my project, which is over here, and now that image.gif is there, and now I'm going to say image.gif, and then after that I'm going to say the target size, target underscore size, is again going to be a tuple, but we're also going to need those constants, so I'm just going to bring those constants over here and just get the tuple from there and have it like that, and then we're gonna, alright, that's it. And what is this? Did I start the, okay, image width, alright, this looks good, and then we're gonna do image underscore array, which we need to make the image an array. We're gonna do keras dot preprocessing dot image into array, and then inside img is the image, and then image array again is equal to tf.expand and we're image array, and then 0. And let me just explain these lines here. We're loading in the image using keras preprocessing load image, and then we are converting that image to an array, and then we are expanding that array using expand dims to create a batch, because model.predict does not accept single images, it requires a batch. So here we're just creating a batch of one image, and then we're going to make prediction. So predictions is equal to model.predict, and we're going to do image array. But first we got to load the model, so model is equal to tf.keras.model.load models, and then just gender.h5, and we're going to do model.predict like that, and then we're going to do score is equal to tf.nn.softmax, and then predictions 0, like this. And once we have that, we're going to print this image belongs to, just like that, format it later, belongs to with a, I'm going to do rather like this, there is a chance the image belongs to, like that. And then just we're going to format it, and in the first parenthesis we're going to do class names, and we're going to do np.argmax score, like that, and then after that, just like this, 100 times np.max of score. And what this does is this multiplies the score by 100 to get a percent. And I just realized we haven't brought in class names, or we haven't defined that. And to define that, we're just going to do class underscore names is equal to female and then male, like that, or like this rather. And I'm just going to make sure that that's in the right order as it was output. So I'm going to scroll up through this training dialog, and make sure I got it in the same order. Oh, right. I guess it didn't log, but it's in this order I'm thinking because it's alphabetical. But once the class name is defined, we have it like this, and I think we need another parenthesis. Yes, and this is what we need, and I'm just going to remove the unused imports now. Layers. So this is really all we need. And now for the moment of truth, let's run this, see what it thinks the image is of. And I get image.gif. I got the extension wrong there. It is actually GFIF, or JFIF, so just correct that, run it, and moment of truth. And yes, there is a female chance that the image belongs to 99%. Okay, so I clearly got the string formatting wrong there. Let me flip that. Whoops. But it did got it right. Let me just correct that. It's funny. Okay. np.argmax score. Just bring that on the other side. All right, let me run it again now. And yeah, here we go. There's a 99 whatever chance that the image belongs to female. So this model seems to be performing pretty well, but that's just one image. So I've already tested this, and I will test it off screen before we, or off camera before we go to the next one. But you can just come, this person does not exist, and just like hit F5 and like download the images and test it out. But yeah, that's going to be it for this video. Make sure that you subscribe and enable notifications so you don't miss the future parts to this series. And if you like this video, click the like button, and I'll see you in the next video.